Welcome to an introduction to Alpamayo-R, NVIDIA's 2026 Vision Language Action Model for self-driving. Its whole idea is right there in the subtitle, bridging reasoning and action for generalizable autonomous driving. In plain terms, a car that pauses on the why. What is that cyclist about to do? Why is the van ahead drifting left? It reasons about the scene first and only then decides what to do. That one habit, think, then act, is what lets it handle a moment it has never seen before instead of freezing the way today's systems do. Over this series, we'll build that idea up from the ground in 4 parts and 15 short chapters, plus a bonus chapter on the frontier. From the basics of how a network learns, all the way to the full driving brain and a little beyond. Let's look at the road ahead. Here's the full map. Don't worry about memorizing it, just notice the shape of the journey. Part 1 is the problem. Chapter 1, the 99% and the 1% is why the long tail matters. Chapter 2 is the long tail problem itself, why plain end-to-end imitation breaks. Part 2 builds the foundations, one piece at a time. Chapter 3 covers the machine learning basics, training, loss, and inference. Chapter 4 is attention, self, and cross-attention across 2 parts. Chapter 5 assembles the transformer block. And Chapter 6 is flow matching, turning noise into a smooth trajectory in about 10 steps. Part 3 is about models that reason. Chapter 7 lays out the family, LLM, LRM, VLM, and VLA. Chapter 8 opens up vision language models and the Qwen 3 backbone. Chapter 9 traces how driving models evolved into VLAs. And Chapter 10 is test time scaling, thinking harder right when it matters. Part 4 is the driving system itself, where every piece comes together. Chapter 11, the bird's eye view and meta actions. Chapter 12, how pixels and motion become tokens. Chapter 13, the multi-stage training. Chapter 14, reinforcement learning and GRPO, getting the reasoning to agree with the action. And Chapter 15, safety in the long tail, 2 paths, 1 tail. And finally, a bonus chapter, Chapter 16, advanced and frontier topics, that steps beyond Alpamayo to where the whole field is heading. Waymo's Emma and its case for demonstrably safe AI, agentic small models, diffusion instead of pure autoregression, and world models. Through all of it, hold on to one idea, reason about why, then act. That's the single thread that ties the whole series together, and it's how Alpamayo-R handles the long tail. One honest note before we begin. This explainer was put together with the help of AI, but it is not purely AI-generated. And a quick word on who it's for. It's written for a mixed audience, project managers, engineering managers, and anyone brand new to AI, so it deliberately ramps from the basics all the way up to the advanced topics, intuition first and the detail later. Wherever something is already familiar to you, feel free to skip ahead. A genuine thank you to NVIDIA, to Google, and to Physical Intelligence, and to the many researchers and companies whose work these ideas are built on. This is an educational explainer. All credit for the underlying research belongs to its original authors, and there was never any intent to take or misrepresent anyone's work. And it isn't just a generated script. It reflects real hands-on work with Alpamayo and with VLA models, some parts of work done together with my colleague Sushin Garg, and we have some working knowledge of the system which was carried out in private capacity. The AI simply helped tell the story. With that said, let's get started. Self-driving cars have quietly become very, very good at ordinary driving. They hold their lane, follow the car ahead, stop at the red light, often more smoothly and more patiently than a tired human would at the end of a long day. But there's a catch, and the whole field turns on it. The real danger was never the ordinary. It's the strange, once-in-a-thousand-miles moment that nobody trained the car for. First, though, let's start with what already works. Watch this car roll down an open road. Nothing unusual is happening, and the system handles it perfectly, keeping to the lane, holding a safe speed, smooth and confident. So why is it this good? Because it has seen this situation millions of times in its training data. Everyday driving is common, there are endless examples of it, so the model has learned the pattern cold. For the 99% of driving that looks just like this, the commute, the highway cruise, the slow crawl through traffic, today's systems are genuinely excellent. Now watch what happens when the world throws something it didn't expect. A person suddenly pushes a trolley out into the road. It's an odd, rare sight, something the car has almost never seen before, and certainly never in this exact shape and lighting. And here's the problem. The car hesitates, then fails. Not because the obstacle is hard to see, the sensors register it just fine, but because the model is at its core a pattern matcher. It answers a new situation by copying what it did in similar past ones. So when nothing in its memory matches a person, a trolley, right there in its path, it has no pattern to fall back on. It can't reason from first principles that a human in the road means stop now. So it breaks down at the worst possible moment. And it isn't just one weird case. Today's models tend to break on a whole family of them. A construction worker waving traffic through by hand against what the lights are saying. An emergency vehicle racing in from a direction you never expected. Cargo that's fallen off a truck and is lying across the highway. Or the mouth of a tunnel where your GPS drops out and the lighting flips in an instant. Notice what these all share. Each one is rare, you could drive for months without seeing it. But each one is also safety critical. When it does happen, getting it wrong can be catastrophic. Rare and dangerous at the same time, that's the worst possible combination. And these are only a handful of examples for intuition. Many more live out in that tale, and whether any one of them trips a model really depends on the conditions. That's the trap. End-to-end models are trained mostly on common, everyday driving, so they have no real framework for reasoning about these unusual events. They've simply never practiced them enough, and you can't memorize your way out of a situation you've never seen. This has a name, the long-tail problem. Picture every situation a car could ever face. A handful of common ones, cruising, stopping, following, happen constantly, and they fill up the training data. But stretching far out behind them is a long tail of rare situations. Each one shows up only once in a great while, yet together, they're the moments that decide whether a system is truly safe. End-to-end models thrive where the data is dense, and they stumble out in that sparse tail, where the examples are few and genuine reasoning is missing. More data helps, but you can never collect enough because the tail is effectively endless. So what's the fix? The core idea of Alpamayo-R is simple to say and hard to do. Teach the model to reason about why, to understand the scene and its causes before it decides what to do. Reasoning first. Action second. That one shift is what the rest of this series is all about. Next, we dig deeper into the long-tail problem. Why end-to-end imitation breaks. In Chapter 1, we saw the symptom, self-driving models break on rare events. Now let's understand the disease, because once you see the cause, the whole design of Alpamayo-R starts to make sense. It comes down to three linked weaknesses. Supervision is sparse, there just aren't many examples of the weird cases. There's no causal reasoning, the model never learns why things happen, only what tends to follow what. And the result is long-tail brittleness, confident on the common, fragile on the rare. Those three feed each other in a loop. So let's see why end-to-end imitation learning falls into this trap and what Alpamayo-R does differently. Driving situations aren't spread out evenly. They follow a power law. A small number of situations, cruising, car following, stopping at lights, happen constantly. That's the tall spike on the left, the head of the distribution. But trailing off to the right is a long, thin tail, a huge variety of unusual events, each one individually rare. Roughly 99% of what you meet is nominal, only about 1% is long tail, but the consequences are nowhere near equal. That 1% is where almost all the serious risk lies. And here's the problem for a model that learns by imitation. Training rewards getting the frequent cases right because that's where almost all the data lives. Every rare event is one faint voice against a million loud ones. So the model pours its capacity into the head and barely fits the tail, exactly the safety-critical part where we most need it to be reliable. So what exactly is imitation learning? The idea is wonderfully simple. Teach a car to drive by copying human experts. You record huge amounts of people driving, every situation paired with the action the human took, the turn of the wheel, the press of the brake. Then you train a network to reproduce those actions. Researchers call it behavioral cloning. The model's whole job is to make its action match the experts. And it has real strengths, it's simple, and it scales beautifully. The more driving data you collect, the better it gets on everyday roads. But look closely at what it actually learns. It copies what the expert did and never why they did it. It sees the brake go on, but not the child it was for. On the rare events, there's barely any data to copy from, so the long tail stays brittle. And the moment the car drifts into a situation no human ever demonstrated, small mistakes start to compound, each one pushing it somewhere even less familiar. There's nothing to fall back on. So how do you build a driving brain? Compare two approaches side by side. An end-to-end model is one big neural network that runs straight from sensor inputs to a trajectory, trained all at once. It's simple, it's scalable, and it's genuinely great on common cases. But it fails in the rare ones. It offers no interpretability. When it makes a mistake, you can't ask it why, and crucially, it only ever learns correlation, never causation. Alpamayo-R is a vision language action model, and it slots one extra box into that pipeline. Sensors, then reasoning, a chain of causation, and then the trajectory. That one inserted step changes everything downstream of it. It buys explicit causal reasoning, interpretable decisions you can actually read in plain language, and the ability to generalize out into the long tail. Here's the heart of the whole chapter, and it's a contrast between two kinds of model. On the left, the memorizer. It learns a direct mapping, pixel pattern straight to trajectory. It works beautifully on examples it has seen, but it falls apart on new patterns, and it has no understanding of why it's doing anything. Show it something genuinely new, and it just reaches for the nearest old answer. On the right, the reasoner. It learns a different habit: observe, then reason, then act. Because it works through the logic, it generalizes to scenarios it has never seen, it handles the long tail, and it can actually explain its decisions in words you can check. That's the line to remember. Pattern matching is not the same as understanding. The memorizer blends old answers together and hopes one fits. The reasoner works out a new one from the situation in front of it. So what's Alpamayo-R's answer? Build a model that explains why before it acts. Instead of jumping straight from pixels to a trajectory, it first lays out the causal story of the scene, what it sees, what matters, and what that implies, and only then chooses how to drive. The reasoning isn't decoration, it's the thing the action is built on. And that's the thread running through this entire series. Causally grounded reasoning leads to better long-tail performance. When the model truly understands the cause, it can handle a situation it has never seen before because it isn't matching a picture, it's following the logic. Reasoning generalizes where memorized patterns simply don't. Coming up next, ML Basics, Training, Loss, and Inference. Before we open up transformers and flow matching, let's take 60 seconds and lay the foundation. Because everything in this series, no matter how fancy it looks, is really just 6 words. Input, weights, loss, gradient, training, inference. Get those 6 and the rest is detail. A neural network stripped all the way down is a machine that takes numbers in and gives numbers out, and the only thing that makes one network smart and another useless is the numbers inside it. Let's walk through how it learns to give good ones. Let's start with the first 2 words, input and weights. Here's a small image classifier. The input is an image, just a grid of pixel numbers. It flows through stacks of learnable filters. That's the convolution, the activation, the pooling, and each stage squeezes the picture down into more and more compact features, from edges to shapes to whole objects. Then a fully connected layer takes those features and turns them into a prediction, a score for each possible answer. Here the model says 0.7 for class 1, its best guess. Now here's the key idea. Every single filter and every single connection in that network is a weight, just a number on a dial. A real network has millions of them. And learning, the whole of it, is nothing more than finding the weights that turn raw pixels into the right answer. Third word, loss. How wrong was that guess? We need a number because you can't improve what you can't measure. We take the model's prediction, 0.7, and we compare it to the right answer, which here is 1.0. Then we boil that gap down to a single number. Square the difference. 0.7 minus 1 squared gives 0.09. That's the loss. And the rule is simple. A big loss means the model was very wrong. A loss of 0 means it was perfect. So the entire goal of training is to push that one number down as close to 0 as we can get it. Fourth word, and it's the big one, training. Training is just a loop repeated many times, and every time around it runs in two halves, a forward pass and a backward pass. In the forward pass, an image goes in, runs through the model, and produces a guess, and from that guess, the loss. The backward pass then goes in reverse. It propagates the gradient from that loss back through the network and uses it to update every weight. The gradient is the signal that decides how much and in which direction to nudge each weight, so the network does a little better next time. Forward, loss, gradients, update, and around again. Watch the loss curve slide from high down to low. That whole process has a name, gradient descent. Picture a ball rolling downhill on the lost surface. You're letting the weight settle into the valley, one small step at a time until the guesses get good. And this loop is brutally heavy. Millions of weights, billions of examples, the loop running again and again. So it runs on racks of data center GPUs wired together, for example, NVIDIA H100 or GB200 clusters. Huge memory, peak throughput, days or even weeks of compute. But here's the consolation, you pay that cost just once. Fifth and final word, inference. This is the part where you simply use the model, the part that actually drives the car. Training is finished, so the weights are frozen, locked in place, never changing again. Now you feed in new data the model has never seen, run it forward exactly once and read off the answer. No loss, no update, just a single, fast forward pass. And notice this runs on completely different hardware. Training lived on data center GPUs. Inference lives on one lean, power-sipping chip inside the vehicle, NVIDIA Drive Orin or Thor. Because this is what runs every time the car sees a new frame, tens of times a second. For the whole drive forever, it has to be quick and it has to sip watts. Train slow and expensive once. Deploy fast and cheap always. So let's put the 6 words back together. Input, the numbers you feed in, pixels, words, sensor readings. Weights, the millions of dials inside, that is what the model knows. Loss, one number scoring how wrong a guess was. Gradient, the signal that moves each weight, computed from the loss. Training, repeatedly nudging those weights downhill to shrink the loss. And inference, weights frozen, one fast forward pass on new data. That's it, everything's still ahead in this series, the vision transformer, the vision language model, flow matching, reasoning, all of it is just these same 6 ideas, scaled up to billions of weights and wired together in clever ways. Keep them in your pocket and let's go build the machinery. Coming up next, attention, self, and cross-attention. Every part of Alpamayo-R, the vision encoder, the reasoning backbone, the trajectory decoder, is built from one idea, the transformer and its engine, attention. Learn this one mechanism and you've learned the part that shows up everywhere. So let's build that idea up from scratch in plain language. No prior math required. A transformer is, at heart, a beautifully simple machine. It reads a sequence of things, words, image patches, sensor readings, and works out which of those things are most relevant to each other. That's really it, everything else is detail. The magic is in how it decides what's relevant, and that mechanism, the thing we'll spend the rest of the chapter on, is called attention. Before we crack it open, here's the whole job of attention in a single picture, as one box. On the left, a sequence of token embeddings goes in one vector per word. The car, it, light, each carrying only that word's own meaning. They pass through a single box, attention, which lets every token look at every other and mix them together. And on the right, out comes the same number of vectors, but now they're context vectors. Each one is its own token, plus the relevant context pulled in from the rest. Same length, far richer meaning. Watch it. On the way in, it's just a vague little vector. On the way out, it's almost identical to car. The box has copied the meaning of car straight into it. That's the whole job, turn standalone meanings into context-aware ones. And inside that box, it's just query, key, value, and a softmax, which is exactly what we open up next. So how does a token actually decide what to focus on? Through three roles: query, key, and value. Think of it like a little search engine running inside the sentence. Each token forms a query: what am I looking for? Every token also offers a key: here's what I have to offer, and a value: my actual content. The model compares one token's query against all the keys, and strong matches get high weights. Then it blends the values together, weighted by those matches. Query finds the match, key advertises it, value carries the information. Three simple roles, and attention falls right out of them. Let's make that concrete with one tricky little word. Take the sentence, the car stopped because it saw a red light. What does it refer to? You and I know instantly it's the car, but the model has to discover that from scratch. So the query from the word it goes hunting across the sentence, and it lands most strongly on the key from car. That connection lights up, and it inherits the meaning of car. That's attention resolving meaning from context automatically with no grammar rules handwritten in. So what does a token actually walk away with? A context vector. Once the attention weights are set, the token takes a weighted sum of all the values, mostly the ones it attended to strongly. That blended result is the context vector, a fresh version of the token now enriched by the words around it. It came in as a generic pronoun, and it comes out carrying the meaning of car. And every token gets upgraded this same way in light of its neighbors, the whole sentence quietly sharpening itself all at once. And here's what makes transformers so powerful and so fast. All of this, every token forming its query, scanning every key, blending its own context vector, happens for all tokens at the very same time in parallel. Older models had to crawl through a sentence word by word, like reading with a finger on the page. A transformer takes in the whole sequence at once. That parallelism is exactly why these models scale to enormous sizes and still run fast enough to drive a car in real time. Now let's back all the way up. How does text even get into the model in the first place? Because a network only speaks numbers. It takes 4 steps. First, the English text is split into tokens. On screen we keep this simple, roughly 1 word per token, but in practice the tokenizer is smarter. Schemes like BPE byte pair encoding break words into subword chunks learned from data, so stopping might become stop plus ping. Each token then maps to a token ID, just an integer from a fixed vocabulary. And for text, those vocabularies are large, tens of thousands of tokens, from around 50,000 in GPT-2 up to roughly 151,000 in Alpamayo's Qwen3 backbone. That ID looks up an embedding, a long vector of numbers that captures the token's meaning, where similar words sit close together. And those embedding vectors are what attention actually operates on. Pixels and motion get turned into tokens the very same way. And that's what lets one single model read everything at once. Now let's slow the whole thing down and watch attention work end-to-end on 3 tokens: car, stop, and it. Step 1. Projection. Each token's embedding is multiplied by 3 learned weight matrices. WQ, WK, and WV stack the 3 tokens, and it's just 3 clean matrix multiplies. The embeddings times WQ give the full query matrix, times WK the key matrix, times WV the value matrix. The query is what a token is looking for, the key is what it advertises to others, and the value is the content it hands over. And those 3 weight matrices are the only part that's actually learned. Training shapes what each token asks for, what it offers, and what it carries. Step 2. Scoring. Every token's query is compared against every token's key with a dot product. A high score means this key is a strong match for what I'm looking for. Step 3. The causal mask. While the model generates text, a token is only allowed to look at itself and the tokens before it, never the future, because the future hasn't been written yet. So we blank out everything above the diagonal and the attention matrix becomes a triangle. Car can see only car, stop can see car and stop, and it can see all 3. Take that mask away and the model would cheat, reading an answer it hasn't written yet. Step 4. Normalize. Each row of scores is squashed into weights that add up to 1. That's the softmax step we'll zoom into next. Read the rows. Car attends fully to itself 100%. It has nowhere else to look. Stop splits 47 and 53 across car and itself. And it spreads 29, 33, 38, leaning most on itself while still pulling in context from car and stop. Step 5. The blend. Each row of weights multiplies the value matrix, and out comes that token's context vector, a weighted mix of the values it was allowed to see. 3 tokens in, 3 context-enriched tokens out, each one now carrying the meaning of the words it's permitted to attend to. One small but crucial piece turns those raw matches into usable weights, softmax. When a query gets compared against all the keys, you get a list of raw scores, some big, some small, some even negative. They don't yet add up to anything meaningful. Softmax squashes them into clean attention weights, all positive and adding up to exactly 1 like slices of a pie. And bigger scores get exponentially bigger slices. So softmax is what converts how well did these match into how much of my attention each token actually gets. Generating token by token hides an expensive little problem. Every time the model adds a new token, the naive approach would recompute the keys and values for every previous token over and over across the whole sequence. The longer the text gets, the more it redoes work it already did a moment ago. That repeated work piles up and generation slows to a crawl. For a car that has to decide in milliseconds, that kind of waste is simply unaffordable. So transformers pull a trick. Well, the trick is the KV cache. A token's keys and values never change once it's been processed, so compute them once and store them. When the next token arrives, it only has to compute its own query and then attend against the keys and values already sitting in the cache. Compute once, attend forever. It turns redundant recomputation into a quick lookup. This is a big part of how Alpamayo-R hits its 99 millisecond real-time latency. And in Part 2, we'll take all these pieces and build the specific kinds of attention that power the model. Coming up next, Attention Part 2, Multi-head and Cross-attention. We've got the basics of attention, query, key, value, softmax, the cache. Now let's turn that into a real toolkit, because the same mechanism shows up in 3 different flavors, depending on where the queries and keys come from. Self-attention, a sequence looks at itself. Every token weighs every other token in the same sequence. Cross-attention, one sequence looks at another, queries from A, keys and values from B, and multi-head attention, many attention patterns running in parallel, each catching a different relationship, then merged. Same engine each time, just wired up differently. Let's take them one at a time, starting with self-attention. First up, self-attention. Every token looks at every other token in the same sequence, building context from within. The key thing, query, key, and value all come from the same place. Here's an analogy: the honest student. Picture a student at their desk during an open book exam. The exam question is the query. Their own stack of books, each with an index, are the keys, and the contents of those books are the values. The student asks, which of my books has the answer? And book 2 lights up at 88% with a little from the others. The answer is a weighted blend of all the books, leaning hard on the best match but never ignoring the rest. The whole point, query, key, and value all come from the same desk. The sequence is studying itself. Here it is live. Watch as each token lights up in turn and the arcs show where its attention flows. The thicker the arc, the stronger the focus. And this is exactly what happens inside Alpamayo-R's vision encoder. Each image patch attends to the other patches in the same camera frame, so a wheel patch latches strongly onto the car body right beside it and weakly onto the sky far away. That's self-attention, building up an understanding of the scene from within a single image, patch by patch. Now the second flavor, cross-attention. This time one sequence looks at a different sequence. The queries come from A, but the keys and values come from B. So if self-attention was the honest student, cross-attention is the copying student. Student A has the exam paper, that's the query, but it peeks over at student B's books for the keys and the values. A's question reaches across to B's books, finds the best match, book 2 again at 88%, and blends B's content into A's answer. Two different desks, two different sequences, A asks, B answers. This is how a model lets one stream of information consult another. And in Alpamayo-R, this is precisely how the trajectory decoder works. Its queries reach across to the keys and values of the chain of causation reasoning. Let's see that one live too. As each trajectory waypoint lights up, you'll see which reasoning tokens it's reaching for. The flow matching decoder cross-attends to the chain of causation trace. It's essentially asking, you said nudge left for the trolley, so what path should I flow toward? The queries come from the trajectory side, the keys and values come from the reasoning tokens. That's the link that ties the driving directly to the reasoning. The reason and the maneuver can never drift apart because one is literally reading the other. Let's line the two up side by side. Self-attention is the honest student. Query, key, and value all from the same sequence. Its job is to understand context within one source. In Alpamayo-R, that's the vision encoder, image patches attending to image patches. Cross-attention is the copying student. Query from sequence A, keys and values from sequence B. Its job is to connect two different sources. In Alpamayo-R, that's the flow matching decoder reading the chain of causation trace. Same machinery, bolt for bolt. The only thing that changes is where the keys and values come from, and that one choice is the difference between understanding and connecting. And the third flavor, multi-head attention. Instead of running attention just once, you run several patterns in parallel, each head learning a different relationship, and then merge them. Here's the mechanics. Take one token's embedding and slice it up. Say the embedding has 8 dimensions and we want 4 heads. We give each head just 2 of those dimensions, 8 divided by 4. Each head projects its slice into its own little query key value subspace, runs the full attention dance, scores, softmax, weighted values, and produces its own output. Then we concatenate the 4 outputs and project them back into one. Here's the elegant part. Because each head only sees a fraction of the dimensions and they all run in parallel, 4 heads cost about the same as one full attention pass. You get 4 specialists for the price of one. So why bother slicing it up? Because each head can specialize, and the picture I love for this is an octopus. An octopus has 8 arms and each one grabs something different at the same time. Multi-head attention is the same. Take the sentence, the octopus changed color after it spotted the shark. Every head reads that same sentence but asks a different question about the word it. Head 1 handles coreference, which entity is it, and points to octopus at 91%. Head 2 tracks syntax, Head 3 chases semantics, what triggered the reaction, and points at shark. Head 4 watches position and adjacency. No single head sees the whole picture, but together they do. Then all 4 perspectives get concatenated into one rich context vector. That's exactly what Alpamayo-R's Cosmos Reason backbone does, many layers, each with many heads, simultaneously grabbing spatial relationships between camera patches, temporal ego motion, and language command meaning. Like the octopus, every arm works at once. Let's gather up everything attention has given us. The transformer reads sequences and learns which elements matter, all through query key value attention. Self and cross attention let the vision encoder understand a single frame and let the trajectory decoder read the reasoning. Multi-head attention runs several patterns in parallel, object grouping, lane geometry, motion, then merges them. And the KV cache makes autoregressive decoding cheap. Each new token costs order n, not order n squared. In Alpamayo-R, that's the difference that lets it generate its reasoning trace hundreds of times more cheaply than naive attention. The gap between real-time and far too slow. Coming up next, the transformer block, assembling the architecture. We've spent a lot of time on attention, but attention is only one piece of a transformer. On its own, it can mix information, but it can't tell order, it can't stay stable when stacked deep, and it can't think about each token by itself. So around it sit 3 more parts that turn it into a real trainable architecture: positional encoding, ADAN norm, and the feed-forward network. Order, mixing, stability, and per-token compute. Let's assemble the full block. Let's start with where it all began, the 2017 paper. Attention is all you need. The original design had two stacks. The encoder reads, it takes the whole input at once and lets every token see every other through self-attention, building a rich representation of what was said. The decoder writes, it produces the output one token at a time, looking back at what it's already written and reaching into the encoder through cross-attention to stay grounded in the input. One stack to understand, one to generate. Now most modern large language models, including Alpamayo-R's Qwen 3 VL backbone, keep only the decoder stack, because it turns out one stack can do both jobs. But cross-attention doesn't disappear. It comes back later when the trajectory decoder reads the reasoning trace. Before we zoom in, here's the whole block at a glance and notice the direction. Inputs flow up from the bottom, outputs come out the top. At the bottom, the input plus its positional encoding goes in. Then multi-head self-attention wrapped in ADAN norm. Then the feed-forward network wrapped in ADAN norm again, and that's one block. Four ideas working together. Positional encoding injects order, self-attention mixes context across tokens, ADAN norm keeps the deep stack stable, and feed-forward does the per-token thinking. Then you simply repeat this identical block, 12, 48, 80 layers deep, and you have a transformer. The same small recipe copied over and over is all there is to it. Now let's study each piece in turn. First piece, positional encoding. Here's a subtle problem. Attention on its own is just a bag of tokens, it's permutation invariant. Shuffle the words and it computes the same thing. It literally cannot tell dog bites man from man bites dog. Same tokens, very different meaning. So we have to give order back. Alongside each token's embedding, what the word means, we add a position signal where it sits in the sequence. The original transformer used fixed sinusoids of different frequencies, a unique fingerprint for each position. Most modern LLMs use learned positions, and the scheme Alpamayo-R uses rotary positions, or Rho-P, has a lovely twist we'll look at next. Take any of this away, and the model goes completely word order blind. So here's that twist, rotary position embeddings, Rho-P, the scheme Alpamayo-R's Qwen 3 backbone uses. Most methods add a position vector. Rho-P does something more elegant. It rotates each token's query and key by an angle set by its position. Picture a little clock hand for a pair of features. At position 0, no turn. At position 1, rotate it by some angle. Position 2, twice that. Position 3, 3 times. The hand spins a little further the later the token sits. And different feature pairs spin at different speeds, fast hands and slow hands, so together they stamp every position with its own unique angle. Now here's the magic. Because attention compares a query and a key through their dot product, and both have been rotated, the rotations partly cancel, and what's left depends only on the difference of their positions, m-n. In other words, the model doesn't feel absolute slots. It feels how far apart two tokens are relative distance for free. Nothing is added, the vector's length is untouched, and it all happens right inside attention. That relative distance property is a big reason rotary positions have become the modern default. Next, the plumbing wrapped around every sublayer, add and norm. The name says exactly what it does. Add the original input back onto the sublayer's output, then normalize the result. It sounds like a technicality, but without it, deep transformers simply wouldn't train. Watch the green arc. Instead of forcing each sublayer to rebuild the token from scratch, we carry the original input forward and just add the sublayer's small correction back onto it. That residual is a gradient highway. It's what lets you stack dozens of blocks deep without the signal vanishing on the way through. Then layer norm recenters and rescales each token's vector mean 0, variance 1, with a learned gain and bias. It keeps the activations well conditioned, so training stays stable and fast no matter how deep you go. Together, ADAN norm is the plumbing that makes a deep transformer learnable at all. The last of the four pieces. Attention mixes information across tokens, but mixing isn't enough. After gathering from its neighbors, each token also needs to be processed on its own. That's the feed-forward network. It's the same little two-layer network applied independently at every position. It takes the token, expands it into a hidden space about 4 times wider, applies a nonlinearity, a GLU, and then projects it back down. That brief expansion is where per-token computation happens, room for the token to be transformed before it's squeezed back. And here's a fact that surprises people. These feed-forward layers hold roughly 2/3 of all the model's parameters. This is where most of its stored knowledge actually lives. So that's the textbook block. Now let's look at the real thing. One block of Qwen 3, the backbone Alpamayo-R actually runs. Same 4 ideas, just in their modern, more efficient form and still reading bottom-up. Notice its pre-norm. We normalize before each sublayer and add the residual after, which trains more stably than the original post-norm order. The normalization is RMS norm, a cheaper, bias-free cousin of layer norm. Attention is grouped query attention, where many query heads share a few key value groups. That's most of multi-head attention's quality at a fraction of the memory, which matters for long context and fast inference. Position is row P applied right inside the attention. And the feed forward is SWI glue, a gated variant that's a richer nonlinearity than a plain GELU. 4 familiar jobs, sharper modern parts. Now wrap that stack of identical blocks between 2 things: a token embedding layer at the bottom and a linear output head at the top that turns the final vector into probabilities over 151,000 vocabulary tokens. And worth noting, there's no separate position layer here. Row P lives inside each block's attention. That's it. The only thing that really changes as you scale is how many blocks you stack and how wide they are, from 28 blocks in the small models up to 64 in the largest, while the vocabulary and the context windows stay the same. Bigger just means taller and wider, not a different design. And Alpamayo-R's backbone is exactly this, Qwen 3 VL, in 2 and 8 billion sizes, a vision language variant of this same stack, with an image encoder feeding visual tokens in write alongside the text. So let's do a final roll call, what each piece does and what breaks without it. Positional encoding adds a position signal, pull it out and the model is word order blind. Self-attention lets each token gather from all the others, pull it out and the tokens are isolated islands. Add-in norm gives stable gradient flow, pull it out and you simply can't train deep. And feed-forward does the per-token nonlinear computation, pull it out and the model collapses to something linear and low capacity. 4 parts and the block falls apart if anyone is missing. Alpamayo-R's vision language backbone is exactly this block, stacked deep. Attention to mix, feed-forward to think, all wrapped in the plumbing that keeps it learnable. Coming up next, flow matching noise to a trajectory in about 10 steps. We've seen how Alpamayo-R reasons. Now, how does it actually produce a trajectory, not by picking from a menu of fixed paths, but by drawing a fresh one each time? It uses a technique called flow matching. It generates a smooth, kinematically valid driving path out of pure random noise in just about 10 steps. Noise to data through a velocity field by simple integration. It sounds exotic, but each piece is simple. Let's build it up. First, a question: where do driving trajectories actually live? They're not random, they cluster into a multimodal distribution. Think of a car at an intersection. It can go straight, turn left, or turn right. All 3 are valid, all 3 are safe, and all 3 are completely different. Averaging them would drive you straight into the curb. That's what multimodal means: several distinct, sensible answers, and you must commit to one. So here's the setup. We start from pure Gaussian noise, and our goal is to learn how to transform that noise into the distribution of valid driving trajectories. Now here's the clever trick. Instead of trying to model that complicated distribution directly, which is brutally hard, we learn a continuous transport, a way to carry noise to data, parameterized by a time variable t that runs from 0 to 1. At t equals 0, you have a sample of noise. At t equals 1, you have a real trajectory. And in between, every particle smoothly travels along its own path from one to the other. We learn the journey, not the destination, and that turns an impossible modeling problem into a simple one. What guides that journey? A velocity field. A velocity field tells every particle at every moment which direction to move and how fast. Think of currents in water carrying each drop along. Follow the little arrows and you flow from noise toward data. And it obeys a conservation law, the continuity equation, which just means probability mass is never created or destroyed as the particles flow. It only gets carried from one place to another. Learn the velocity field and you've learned how to drive noise into trajectories. So what path should each particle take? The simplest possible one, a straight line. For any pair of start and end points, optimal transport theory proves the straight line is the minimum cost path. So we just use linear interpolation, blend the noise point and the data point. It's both the mathematically optimal route and the simplest thing you could write down, and as we'll see, the straightness is exactly what makes generation fast. Nice when those two coincide. And if the path is a straight line, the velocity becomes beautifully simple. It's just the endpoint minus the start point. That single fact gives us three gifts. The velocity is constant in time, the same arrow at every moment, so there's nothing to recompute as t advances. There's no simulation needed during training, you don't have to roll anything forward. And it's an exact, closed-form label, you know the right answer outright for free. Watch the time slider, the orange arrow never changes direction. Now here's something that looks like a bug, but is actually a feature. Two different training paths might cross through the very same point at the same time, each carrying a different velocity label. So which is right? Both. When you train with mean squared error loss, the model can't satisfy both, so it learns their weighted average. And it turns out that average is exactly the correct overall velocity field, the one that bends the flow toward whichever mode is more likely from here. The conflict resolves itself into the right answer. So the training objective is about as simple as deep learning gets. Pick a random noise point, a random data point, and a random time along their straight line. Ask the network to predict the velocity. Compare it to the true velocity endpoint minus start point with plain mean squared error. That's the entire conditional flow matching loss. No simulation, no adversaries, no fuss, just predict this arrow. Compare that to the machinery diffusion or GAN's demand and the simplicity is almost suspicious. Training is done, so how do we generate a trajectory at inference? We start from a fresh sample of noise and we take small steps. At each step, ask the network for the velocity right here, move a little in that direction and repeat. That's Euler integration, follow the arrows step by step from noise to a finished path. It's the same way you'd walk a trail by checking a compass every few paces. The step size is 1 over n and Alpamayo-R uses just 10 steps. And this is the payoff. Why does straightness matter so much? Speed. Diffusion models follow curved, noisy denoising paths, so they have to take tiny steps to stay on track, something like 200 of them to get there. Flow matching on straight optimal transport paths can stride in big steps without falling off the line, only about 10. 10 steps instead of 200, that's a 20-fold saving and a huge part of how Alpamayo-R hits its 99 millisecond latency. Straight lines are fast lines. So how does AR turn its reasoning into the actual motion the car drives? First, it reasons about the scene, the chain of causation. Then the flow matching expert takes over. It cross-attends to the model's memory, the cached camera tokens, the motion history, and that reasoning, and denoises a smooth, continuous trajectory straight from noise. So the reasoning literally conditions the motion. Change the reasoning and the path changes with it. That's the plan the car drives, produced in a single pass inside the 99 millisecond budget. And if you want diversity, you can sample several reasoning rollouts at once, tuned by temperature, top K and top P, to get a handful of distinct candidates, then reconcile them into one plan. But by default, AR reasons once and drives the trajectory that follows. Let's compress the whole idea into 5 lines. 1. Driving trajectories live in a multimodal distribution. 2. Instead of modeling it, learn a continuous flow from noise to data. 3. The optimal path is a straight line, so the velocity label is just endpoint minus start. 4. Train a network to predict that velocity with simple mean squared error. And 5. At inference, start from noise and follow the velocity for 10 little steps. 5 lines and you've got the whole method. That's flow matching. and it's how Alpamayo-R turns randomness into a smooth, drivable future. Coming up next, model types LLM, LRM, VLM, and VLA.